Hi, you're not late. I think everyone's waiting to get in the room. I think he teaches a class next door, so everyone's waiting to get in there. Mm. Well, 12:30. I guess I'll just start this stuff. Do you have any problem with the homework or anything? Did you look at it yet? No one's turned it in, so I think maybe no one's looked at it.
Yes. During the activities, but we just did all of the values and recorded and use the equation solve for.
Yeah,
Okay.
yeah, it's algebra, I think.
Okay.
Yeah,
Just computed person.
yeah, no, you have to calculate it. Yeah, yeah, you have to go through the calculation and then I think you just, I don't think they list the modulus. I think you got, find it on the internet or something. Maybe they list it somewhere, but it's not. Uh, Well, anyway, so I wanted to finish the heat capacity today and then go through, maybe start the next section. See, I gotta be at 78 here. There's a lot of slides. This is following the book mostly. So, and he kind of goes through a bunch of different things topical. So it's like topic. And they aren't necessarily coherently connected together in a sequence of logic, so but they are, I think if you look in the literature, all of them are important. Like people use, so you can find papers on each one of these things. So it seems worth going through it like that. Um, let's see. Yeah, so I had 78 is where we left off, but so anyway, this Grun-Eisen parameter, actually, I think I did, I can't remember if I did this or not, but basically, this Grun-Eisen was a German in 1877 or something like that. And then he came up with a few equations in this parameter, and the parameter is how the frequency of a vibration, so like a phonon changes with the specific volume, like the density. So as it becomes denser, the frequency goes higher. That's the idea. So so 1/V is rho, like the density. And that's kind of the definition of his Brun-Eisen parameter. And it turns out this thing ends up being related to CP, and also this thing's related to CV. So because it's related to both, then you can get the difference between CP and CV in terms of that parameter. So you have that kind of is how you define this thing. Right. So you can look up that parameter for different materials and you can get the difference when you don't, this is in the case where you don't know the compressibility, but you know the thermal expansion coefficient. So CV is the thing you can get from theory, like Einstein or the Debye. Then you want to get CP. Again, like at low temperatures, they're the same. And then there's only a small difference when you get the high temperatures. So it's kind of like this is almost like an adjustment, of CV to get CP. So anyway, so then, so like I said, it's topical things in here. So the next topic is like, how do you get the, how do you calculate the heat capacity if you know the density of states? So this is a separate subject. So there's a bunch of separate subjects. In fact, there's like 50 separate subjects in here, I think. So if you want to get specific heat, if you know the density, so where you get the density of states from spectroscopy. So you're going to have IR spectroscopy is like here. And then you have all right, so you have Raman is this one, IR is this one. So this is transmittance. So usually you can plot transmittance or absorbance. This is plotted as transmittance. So you have it's kind of so you have e to the minus the thickness, the absorption coefficient times the thickness, like L or something. So you get a sample and you shoot through it, it's thickness L. And then I by I naught. So you have your sample, so you have a beam, it's got intensity I, and you measure I transmitted through. So you have the transmitted is going to equal the absorption coefficient. And then the transmittance is going to be, transmittance is like I minus I naught minus I. That's the transmittance that is shown here. Would be percent transmittance be like that over I naught. And then down to 100 or something. So anyway, the things are related. This thing comes from the idea that you have that the beam change is going to the delta I that's going to happen is proportional to the I that came in. I'm not right. So delta I. So you end up with BI by I, and then that times the absorption coefficient. So BI by I. If you integrate that, you'll end up with like ln of I by I naught equals alpha. So that ends up or minus. It's negative. It drops. So anyway, that's how you get this E thing. So it's called a linear absorption, even though it's an exponential function, right? Because it's a linear, the change in intensity proportional to the intensity is linear. It's linear intensity times the thickness of the thing. Or L I used here. So anyway, so if you want to convert transmittance, this T, you can convert the transmittance to the absorption. But they aren't so in this case, anyway, absorption is the thing you usually plot. So when you run an IR, you can plot it as transmittance or absorbance, and it'll be like this curve, one upside down. So this is actually the absorbance for Raman. Like he's saying intensity, but it's absorption intensity. Because Raman's measuring this shift, right? So you get the frequency from the distance. So you have the beam that went in, 785 nanometer, 0.785 micron wavelength. So it's like green, I think. So green laser goes in, it's got a spike. And then there's these side things that have to do with Brahman, have to do with the bond vibration. So you have some kind of bond vibration that it can absorb the energy and give you the Stokes. So you get a lower frequency for the Stokes, or the bond could already be vibrating. It can contribute to the light. Then you get a higher frequency. To get Stokes and anti-Stokes, there's a symmetric pair of peaks shifted that are associated with the vibrations of the material. If that's in the gigahertz range, so if it's a small energy change, then basically that's a Brillouin scattering, and that has to do with groups of atoms, like in a acoustic vibration where the atoms move, or they're compressing and decompressing, like in a longitudinal wave going through the system. So that'll be like a Brillouin, and then if it's a vibration of the bond, that's a much higher energy. So that this distance would be off scale here. It would be like 100 times bigger than that. So it'd be, I don't know what 100 times minus 40 would be, but it's somewhere over here, right? So both things, the Brillouin and the Raman use the same laser, like using the 785 nanometer laser. Right, so the difference is in the optics of the detection. Like the detection is going to be low energy detection for the shift, and the brilliant and high energy detection for that shift in Raman. And they're both seeing symmetric peaks. They both have Stokes and anti-Stokes peaks to them. Right. So this was 1877 for beryllium, and then like 1912 for Raman, and the laser was invented in 1967. It's like somehow they did this without lasers. I don't know exactly how that worked. I think it must be at first it was like a theory. So they came for kind of a theory. All right, Raman's like the most famous Indian scientist, right? He's like the god of Indian science. So that's another little twist to this thing. So apparently he was a really brilliant person. Like Einstein wanted to meet with him, all this stuff, like the stories about it. So anyway, but still, when you look at it, like Brilliant was 30 years before, and it looks like exactly the same thing. So I'm not sure if Einstein wanted to meet with Brilliant, but probably did. I mean, Brilliant, I think, worked with Bloch and some of those other people, like famous 1800s physicists, whatever. So anyway, so that is what it is. So anyway, there's a machine that does this measurement in Neil and John Nichols' lab downstairs, and he said, so two of you guys said you wanted to go see it. So and you said 2 o'clock tomorrow, right? That's so anyway, he said he could do it. So that's good. So we can do that. If anyone else wants to. 2 o'clock, and it's in the fourth floor of Rhodes. If you go all the way to the end of the hall like that towards the football stadium, then there's a lab that you would walk into. It's in that lab, like where the bathroom is. There's like a woman's room, men's room. It's like straight right there. I don't know what the number is. It's probably 405 or something. What are you guys doing? Do you guys, I don't know, it's up to, it doesn't matter to me. Oh, 12:30? Oh, okay. All right. I'll tell him 12:30. I'll see if that's okay. I don't think it matters. Hopefully it doesn't matter. I thought you had said 2, so I just said 2. All right. Okay, I forgot about it. I mean, in fact, he said he couldn't do it because he was going to be in, so he does. So this technique of looking at the vibrations with this laser thing, so they also use neutrons to do the same thing. So a neutron can come in and absorb this same kind of energy. So you can go to a nuclear reactor or a spallation source. Spallation source is like they'll have like you have some kind of particles, like I think they use positrons, and they shoot them under high energy and they blast them into a piece of metal. And then the metal shoots off all kinds of mixed radiation, but sometimes it shoots off neutrons. And this will be like a light bulb. It's a broad spectrum. If you do the density versus light energy, then you're going to have like a really broad spectrum. So basically, neutrons have mass, so that the energy of the neutron is related to half mv squared. So you get a velocity. So you have a velocity. So that if you shoot down along the tube, the high energy ones get there first, and the low energy ones, like poking along, get there later. So if you pulse this thing, this is a pulsed laser. You pulse it like 60 hertz, and you have like 36. But it doesn't end up. Anyway, you get 60. You can take time slices every 1/60th of a second, which is like 0.02 seconds, I think. So you have the whole spectrum you get in 0.02 seconds with the time resolved. So you slice this into times, because h nu is the velocity, and you get there later. So you're going to detect like start and end detection, get all the spectrums that way. That's called spallation source. That costs 1 billion to build that machine that he uses. So it's an expensive thing. The other thing you can do if you want to get neutrons like that is build a reactor and just have you can also have a velocity selector here and pick out just one wavelength with one energy. And just get a single energy from it. by tuning the velocity selector. Nuclear reactor is kind of also like a light bulb. You get a broad spectrum, but you can usually pick one peak wavelength off of it. Anyway, so it Oak Ridge is both of those. There's a thing called S and S, and this thing's called the IPNS, intense pulse neutron source. This is 60 megawatt. So basically, a power reactor, like a modern power nuclear reactor, is like 150, 200 megawatt, and a normal research reactor is like 1 megawatt. So it's like a huge reactor use, I mean, for this kind of experiment. But and then this thing, this SNS is the spallation neutron source. Right, so the neutrons come in and interact with the phonons and also take off energy and move the spectrum from that. So that's what he was doing going to Oak Ridge. He used $1 billion machine, but they canceled it, so he's here on Wednesday. So he's kind of like traveling there. There's also this stuff at NIST in DC, and that's it in the US. There's 2 places in Oak Ridge, one in NIST, and then you can go to Europe. You can go to Grenoble or to a place in Oxford, England. There's a couple other places you can go. There's like a few places around the world where you can do that. And then you have to be kind of interested in this kind of spectrum thing to do it. So it's a little bit of a, anyway, it's a thing people do. It's a big money thing, you know, so it's kind of like, it's a big science thing, like a big telescope or something what people use. Anyway, so that's tied to this. Like, so why they're going there is to get these energy spectra so they can do this kind of analysis of crystals, more or less. I mean, you can also do it with membranes. Like if you want to look at biomaterials, you can use this stuff too to look at the dynamics of molecules transmitting things. Anyway, Nichols is an expert at that kind of stuff. So maybe you can talk a little bit about it. Anyway, so yeah, so you use spectroscopy, then you could get, from that, you can convert that to the density of states. And then you can, once you have the density states, then you can get the heat capacity. So to get the heat capacity from density of states, you do an integral. So you have du dt, and then this is going to be like the Einstein, Bose-Einstein statistics, and then the energy of that one state, and then d would be the how many are at that energy, like the multiplicity of that energy density of states. And then you integrate each energy, how many, and then times the statistics gives you the heat capacity of it. So anyway, so it's just this integral, like this is the Einstein equation for heat capacity with the density of states, but to integrate to get the heat capacity, right? And then you get the heat capacity from the spectroscopic measurements. And I mean, I guess an advantage of that is you can break apart, if you know the mode's vibration, you can say what contribution each mode has to the heat capacity at each temperature. So kind of how, like in the paper, I guess maybe last week's paper where he's showing the activation of the different energy levels, right, for graphite and diamond. And you see how the materials behave. You get a different picture, like understanding about how the energy's going into the material, right, and how it behaves. Like a thermodynamics that is all governed by that. Anyway, it's a way to understand materials, right? And then breaking it down into the components gives you a little bit of knowledge base about maybe how you make the materials, more like how they behave, like why do the materials behave the way they do thermodynamically, right? So, but anyway, that's, hopefully you can see there's some kind of use to this. I mean, it becomes really useful if you're trying to make single crystal microelectronic devices, stuff like that, right? Or maybe even alloys, where you have single crystal structures that are going to have these discrete energy bands, right? For if it's like biomedical stuff or things like that, maybe it's, so there's different fields people work in, right? So this is a specific kind of area, like low temperature superconductors. This is like the whole game, right? So it's basically depends what you're interested in, but it's good to have a rough idea what people are doing. That's what you should get out of this. Just a ballpark, you know, some of the terms, you know, what an optical mode, acoustic mode, transverse longitudinal vibration, why you'd want to do brilliant scattering, why people are going to this neutron place to do this stuff. Kind of not totally why, but roughly why, just like it exists. That's good enough. Like you don't have to be an expert in this. I mean, right, this plot just shows like how, maybe I showed this already, but basically it's a nice plot because it's got I guess for this ferroelectric lead, I don't know what SC, tantalum oxide. What is it? Scandium. Yeah, I don't know what that is, but anyway, scandium. Yeah, so it's an oxide. Anyway, it's just showing you can see all the different modes and the acoustic, like the beryllium is way. So this is what 2 orders of magnitude to the lowest optical energy. So optical vibrations are much higher energy. So it's like IR and Raman would give you these. IR gives you the ones if you have like a salt and it's polar, so the polar bonds light up in IR, and then Raman gives you the things we have electron mobility in it. So if you have like conjugated double bonds, like in graphene or buckyballs or nanotubes, like you do. So if you're going to look at nanotubes, you do a lot of Raman spectroscopy to understand. From the absorption band, you can tell between, oh, there's like a D band and a B band or something they talk about, and you can tell the difference. I could find a paper on that, but basically you can tell the difference between the different kind of conformations of the aromatic rings, how they're arranged and you can also tell if it's monolayer, nanotube, or multi-layer, which is important. When you manufacture nanotubes, sometimes people say they want to have monolayer nanotubes. It's just one carbon layer for the thing, and then you get the kind of the strongest nanotube. But if you have multi-layer, they become weaker mechanically. And also the conductivity properties go worse, right? So you use Raman scattering because it's conjugated bonds, because the electrons are free. Wherever you have, it's going to be made up of aromatic things hooked together, and then there's going to be alternating like double bonds in it somehow. There's too many bonds here, I think. That's one. And then this would be like that. So these electrons can flip there, then those go there, those go there. So it's like a card game thing. Maybe I'm missing one here or something. So anyway, it's got a resonance structure. That makes it only be a planar. It'll just be planar structure, and then and also it's got this resonance so that the electrons are really actually free to just travel around this thing wherever they want to go. Right, so it's conductive. So basically, and that means that this is polarizable. If I put a field on this, I'm going to get like all the electrons will rush up here. Right, so that means it's polarizable. It's not polar like NaCl is polar. Right, so this is for IR, and this thing would be super good for Raman. This would be invisible in IR. You'd see no peaks at all. And in Raman, it lights up like a Christmas tree. Right, so it's basically like, and usually you're getting a mixture of that kind of bond and that kind of bond. So with the two techniques, you can light up different parts. Again, it's feeling the vibrations of the bonds. I mean, anyway, and beryllium is also, it's the same thing as Raman kind of, except that it's a much larger size scale at the lower frequency. So you can think about like if you have a bell, and if it's a low frequency bell, it's a low tone, that's a big bell. If it's a high frequency bell, that's a high energy bell, that's the IR Raman stuff. And then these are like such low frequencies. This is a mechanical modulus type thing, and this is this kind of spectroscopic understanding of things. Anyway, maybe so Nichols probably has a different thing to talk about it. It's 12:30. Let me write it down somewhere. Forget. Somehow I got like 2 o'clock in my mind. 12:30 should be an easy number to remember. Okay. All right. So anyway, this is that business. All right. So So then if you, so again, like this chapter, the end of this chapter is just topic, 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 like it goes on. There's a lot of topics in it. So this is another topic. So how to get the entropy from the heat capacity, right? So you have, so it's going to just be an integral because you have CP is ds is, so CV is T times ds dt. So if you integrate CV dt over T, you get S, right? So if you have an expression like an Einstein expression for the CV, you can analytically integrate it, get that for the entropy. So you can calculate the entropy if you know the Einstein temperature for heat capacity, which is nice because there isn't really a way to measure entropy. Like you don't have an analytic way to measure it. You can calculate this heat capacity, so you can get these entropies, right? So if you look at the temperature dependence of the energy, you can get the entropy. It's like the derivative of the energy with respect to temperature will give you the entropy, but basically it's not a direct measure of entropy. So entropy is always the thing that you can't get. So here, this is a way to calculate it based on that Einstein temperature, or you can do the same thing with the Debye temperature and end up with an integral. The Debye integral ends up kind of buried in it, becomes a little bit more complicated. Anyway, you can plot that, little plot here, kind of how the entropy would change on your temperature with different Debye temperatures. The low Debye temperature has a high entropy. And the low Debye temperature also has a high heat capacity. That's where we had, like when we were looking at the superconductor thing, and it had 22 and it had a huge heat capacity. Like it was at hundreds, right? Hundreds. Heat capacity of hundreds, whatever that's plotted. But anyway, then you can compare a calorimetric measure of entropy with this calculation, you get the same number. I guess that's the basic idea. Like the circles are the calculated and the lines, I think, are this equation. So the calculated again is like a derivative of the measurement that you did. So it's a little bit odd. It isn't a direct measurement. And then you can also, he mentions this too, that you can get the group contribution method. So this is another thing, like you'll see, especially if you're working with organic materials, you want to know the heat capacity. So you have some like polymers, for instance, then you can, or any kind of organic material, I think. But basically, I think you can also do this for ceramics or metals, more or less. But if you have like, say you have polystyrene, right? And so it's going to be that and then repeated over so much space, and it's going to end with something like maybe methyl group at the end, something like that. So then this number could be like 1,000. It could be 1,000. It's a long chain thing with these groups on it. So, but it's repeating over and over again, right? So you can say like, well, I have an aromatic group, and then I can say CP is going to be like one aromatic plus methylene plus one methylene, and then plus this photon, I guess, whatever. Right. So, and you can so you can tabulate every molecule that there is, and then get a number that works to give you the right heat capacity. That's what the group contribution method means. Like you figure out how to break this apart. The Dutch invented this in like 1950, I think. This became like a major thing for the Dutch. And this guy's in Germany, but basically, well, he's doing it for metallurgy. I think the Dutch did it mostly in organic materials. You know, predict like you can predict the enthalpy, the heat capacity, the entropy, you can predict everything with this. So it's basically just a table of numbers. It's empirical. There's no understanding. It's just like they work out for all these materials, make a table, get the numbers, and add them up, and you get the constant that you want, right? So if you invent a new polystyrene that's got some like complicated molecule over here, then you can still get the heat capacity of something new that you can't measure, haven't measured. Like say you can only manufacture like a microgram of it, or it's a protein or something like that. So you only have a very small amount. Well, this allows you to get the heat capacity of a thing that you couldn't actually measure it. There's not enough material to measure. Or if it's just a dream that you have, like you're going to make something with a huge heat capacity, then how do you do it? You can use that to kind of calculate it. It's almost like before they had machine learning and artificial intelligence, this was like a poor man's way to do it. Like just tabulate these numbers and add them up, and it kind of works pretty well. In fact, it works just as good as machine learning and artificial intelligence, and it's a lot cheaper. You don't need a nuclear power plant to power the AI. So anyway, so he just mentions this. I think there's not really any, he doesn't show it. He references this paper. So I think this is from him because it's 97. So, but you can find group contribution. It shows up, it like peeks its head out every now and then. So it's not going to go away. Basically, people in desperation use this method and it works to get thermodynamic parameters, right? So, I mean, I've used it quite a few times, put it that way, and not proud of it, but basically, if you need to do it, you can do it. So let's see. Entropy correlates with molar volume. So this is just like I said, this chapter is just topic, and this is just another topic. So if you just do the Maxwell equation, they expand the dP/dt using the trivial product rule. This is a thermal expansion coefficient. That's the heat capacity. Then you find out that the entropy change with volume is a constant. Like those two are constants. That means that the entropy goes with the specific volume or the density, 1 over the density. So basically they're going to go in the same direction. These have to be positive. So I mean, this whole thing has to be going in a positive direction. Except for, anyway, so that, I'm not sure what the value of that is. There's a paper about it. But there's I guess the value is that there's cases where it doesn't work. So where that fails, and that's when you have a transition for the material. Like you have some oxidation state change. So something happens with this structure of the crystal, and then this doesn't work anymore, and you have like a jump in the entropy. So you can't, anyway, it's just a nuance, right, that he talks about. All right, so that's another topic. So it's like a bunch of little topics. So this is the thing we already talked about, this electronic heat capacity. So the idea here is that you have the valence band, so in a metal, in a conductive metal, right? So you have, I guess all metals are conductive, but basically you have an average energy level called the Fermi energy level. So in a metal, like we have all these orbital things, right? S, P, E, whatever orbitals. And then when you get, and those are for an isolated atom like copper. So you have like the d orbital of a copper atom, right? But if you start to bring these things together, then those orbitals, like if you plot the energy versus nothing, you just have the energy levels. When the atoms get together, these energy levels get smeared out because the electrons in the orbitals kind of scatter off of other electrons. So the energy of that gets smeared out. So instead of one energy, it becomes broader. Then they kind of merge together and you get bands. You'll have gaps and bands, right? So the valence bands and the conduction bands. There's a gap between them. And so basically, the idea is that the electrons in a metal have an average energy, which is this Fermi energy. And then if you excite above the Fermi energy, they can pop into this conduction band and then be free electrons. If they're a free electron, that means they can vibrate. And if they can vibrate, they give rise to heat capacity. So that means that you have this other component. So for each one of those electrons that have been freed out of that band, so again, like the orbitals existed for an isolated atom, but when they get crowded together, the orbitals disappear, and then suddenly you get these energy bands showing up. Right? So that's the idea, because of the electrons interfere with each other in the different orbitals for the different atoms. Right. So anyway, the Fermi energy is like a number that's like the average energy of electrons in it. Then KT is going to pop an electron from the valence band to the conduction band. over the as they're at the Fermi energy and get some extra energy and it pops it into the conduction band, then that becomes a free electron, which is going to have 3R, three like XYZ. It's going to be free in 3D space times R heat capacity contribution. All right, so it's a low energy transition. So this shows up when you're at low temperature. That's why we saw it like it's plus K plus gamma T, not the Grun-Eisen gamma, which is gamma sub G, but the electron heat capacity contribution gamma. So there's at least two gammas to start with. There's a bunch of, there's also the gamma that's the activity coefficient. So there's three gammas. There's probably more gammas in thermo, even in this section. You know, so it's pretty confusing. They use gamma a lot. This is a different gamma. This is the electronic contribution. So this gamma you'll see in like a periodic table, and you have the by temperature, and then there's this gamma is down here. It's not the Grun-Eisen gamma to figure out Cp minus Cv or whatever the relationship between frequency and density, but it's going to be this electron thing for it. You can see the numbers change quite a bit. In particular, he shows this series. So he does alloys of the series: rhodium, palladium, and silver, right? And they can make a solution, solid solutions. They can substitute in the lattice, and they can get a huge change in this electronic contribution to heat capacity from 100 to like 6. It's a big jump, right? So that group is kind of an interesting one to look at when you make alloys, because you're introducing electrons that can jump above the Fermi energy, become free, get this 3R that contributes a big amount to heat capacity then, you know, at low temperature, right? So anyway, so because it's electrons and are quantum particles, then you get these things like they can be quantized, and then the effect that should be there, this gamma, becomes like 0 or something for copper, like 7, right? So because it becomes a low number because it's quantized, the electrons that are jumping to the Fermi level are quantized, so they only can have a certain energies. So it doesn't contribute this free thing, the 3R, it contributes something smaller. I think that's my understanding of it, right? So anyway, so that's kind of the picture. So there's this thing is, I mean, this is going to be important if you're going to go to absolute 0. Otherwise, this isn't important, right? It's only going to be important below like 50K or something, this electronic energy contribution. But if you're interested in the electronic structure of materials, then it's very important. Like it's a way to measure, actually probe exactly the electronic structure of the materials, right? So it depends what you're interested in. But so anyway, so why this is gamma T? So this is a little mysterious why it's gamma T, right? So you have the energy. So you have the energy is going to be how many of these electrons that jumped up above the Fermi level, and each of them has a KT energy. So the number that are going to jump above the Fermi energy level also depends on KT. So if you're sitting here, how many are going to hop over the wall and get to be free to contribute to 3R? That's proportional to KT. That's like how many were at the Fermi level times KT gives you how many hop the fence and are going to be free. And for each one that's free, they have KT energy. So you end up with KT squared, which if you take the derivative gives you T, which means this thing is a constant because a number at the Fermi levels, it's a material property. Then it's just T. So you have the contribution of the heat capacities, some number times T, let's call the number gamma. Just because we use gamma for everything, right? So anyway, so that's the idea here. It's a little contrived, you know, but basically all right, they observed that it was linear in temperature. I mean, this is obviously how this was derived. Like they observed it's linear in temperature. It doesn't make that much sense because it should be just constant. Then they say, well, it has to be that this thing happens, because that's the only way that you could get it to be linear in temperature. This is how people work. I mean, it wasn't like they knew this, they got that, they got that. It's like they observed this experimentally when they said, how could that possibly be? And they said the only way it could possibly be is if that number is proportional to KT. And then they said, oh yeah, that could be because you have the Fermi level has to jump the wall, KT jumps the wall. Right. So it isn't like things are the way they seem. Like the sequence of events that's presented in a book isn't the same as the sequence of events that happened in the world. Right. So it's important to keep that in mind because you're at the point of in the world and you're trying to get, you're trying to get that description and you're frustrated because you can't come up with an idea like the number that jumped the Fermi level is proportional to T. Like that's not something that should be obvious to you, Maybe it isn't even true. I mean, that's the other thing. Like just because they say it in a book doesn't mean that it's true. There could be another reason why that works, This is a story that seems to kind of make sense. It's a good example of like it's in an arcane little niche of nowhere, But basically you can see how people are thinking, and then it should help you to be able to, when you approach your own problem, not think that you're so frustrated that you can't solve it. Like, because what people have done is like they've gone back. All right, put it this way. Debye had a function for this, like the structure of polymers, something arcane. But basically, the advisor that I worked with was in a cab with Debye, and he asked him if he knew the answer before he derived it. So Debye's like the smartest guy, And he said, "Yeah, of course I knew the answer before I derived it." So that's the thing. Like, so, and then he went back and made this long calculation, like a 20-page calculation to get that answer. And then that was part of his Nobel Prize thing, Basically, he said like he already knew the answer, so he just went back and figured it out, and then told the story backwards from how it happens, right? So don't feel frustrated if you get to something and like you can't get it. You know the answer, but you can't get it, and you're trying to work out. That's how everyone's like guys that won the Nobel Prize did that. So that's kind of how it's not. This is definitely not the scientific method, but it's important to know that the scientific method is a story you tell after you find the answer. Put it that way. It's more of a framework to explain to other people, not so much to discover, right? Like this idea of like, and most discoveries are made by accident, right? So anyway, so that's the function that we had that everyone would use, the Debye dependence and this electronic contribution. This plot is based on that equation, right? So if it's linear in that plot, it's a Debye oscillator, and it's got the electronic contribution to it that gives rise to the intercept, like a non-zero intercept. So the electronic part, because you did CP by T, you remove this, that's just a constant, so that's the intercept, and the slope is T squared, because you do CV by T, so you have T squared here, that linearizes it. That's called linearizing an equation, right? So you guys should have gotten that at some point. Whenever you see some weird plot, you're trying to linearize it for a straight line. So anyway, so this is that group. So rhodium, palladium, and silver are like, can substitute in each other's lattice, so you get a solid solution. And then you can see, so in the book, he describes this as like it's donating electrons, they become free. That's why this gradually increases. And then for whatever reason, it gradually decreases. This is the gamma, which gives the electronic contribution to the heat capacity. It's like a base level. I forget what that is, but the Fermi level, I guess, gives the base thing here somehow. So anyway, that's the series it gives us in the book, the 822. So I guess that's about it for the electronic thing. So there's electronic, and magnetic. Those are the twist things. So the magnetic is this. Like you have you have a dipole, so it's a ferroelectric. You have a bunch of dipoles that are aligned. And then if you can get, so the dipoles are actually electrons spinning, so they have a spin and a vector. And if you can kind of disturb one of them with a magnetic pulse or an electromagnetic pulse, then you can get this kind of like a vibration go through the system. So it's a vibration, so it's going to contribute to the heat capacity. That's the theory. Any vibration will contribute to the heat capacity, right? So that's the magnetic thing. So some kind of picture of the spin phase angles of the spins, and then you just pop in the Einstein equation. This guy get rid of. So you have the Einstein, so that 1/t², and this is the Einstein function with the density of states. So the density of states are going to be the G magnon, they call this. So there's a phonon, this is a magnon. Right, so it's this wave thing going through it is a magnon, and then how many magnons gives each one gives a Einstein contribution. I guess there's no collective interaction or something, so you use the Einstein equation, and that gives you the C magnon. Right, so anyway, that's another contribution. All right, so people are interested in this because because of a bunch of reasons. One is thermal. You can use magnetization to cool. Like if you get to cryogenic temperatures and want to go to absolute zero, at that point you use these magnet cooling systems. So this heat capacity thing becomes important when you're trying to use a magnetic cooling. So you align and disalign the magnets, and that drops the temperature like a couple degrees. And that's enough when you're already cryostatically cooled down to like almost absolute zero. That gets you close enough, So the last step of getting to absolute zero is using magnets like that. That's one thing. The other thing is like radar. So radar and microwave transmissions for cell phones are all like going to involve this kind of microwaves that absorb. Microwaves will excite these magnon transitions, so that can become like if you want to make a stealth bomber to fly someplace, for some reason, then basically you're going to use magnons to do it. So there's money in it for if you want to bomb people or something, So anyway, so that's another magnon. So there's a variety of kind of weird things that people are doing that need this magnon thing becomes important. Again, like it's a niche thing. And so if you want to measure it, then how do you measure it? Well, you measure it with low temperature heat capacity. Then you can definitively say it's there using these tools, right? So anyway, it's not something I hope that you do, but basically there it is. People are doing it, So anyway, so this is business. I showed this earlier, but this is a polymer. This is actually PET, like a water bottle, or the plastic that's on top of these pens, PET. So it's nice because it's got a really clean VSC curve. So this is heat flow. Basically, this is heat capacity if you multiply it by the ramp of the temperature rate. So you have heat capacity plotted against temperature. And then it goes through a glass transition, which doesn't have a peak. And then you heat it up, and there's a clear water bottle, and then it crystallizes, turns white. So it becomes partly crystalline. It's like 80% crystalline. And it crystallizes and you heat it up some more, and then those 80% crystals melt. So there's a melting, a crystallization and a melting. That's why PET is like the best thing to look at. It has all the transitions in it, and they're all relatively close. The maximum temperature here is like 150 C, and the minimum down here is some like zero, just like freezing, something. So it's a glass at room temperature. Actually, this is probably like -30 or something. So it's accessible temperature range. And it has all the features of, you can see if it's an amorphous material, you just see a glass transition. So this thing, the glass transition is one of the topics that he has of the 15, 20 topics in this end of the chapter. But so this is a clean glass transition. So this would be if you did the glass transition at infinitely slow cooling rate or heating rate. So it just shows a nice one heat capacity for the glass, one heat capacity for the liquid. And there's kind of a sigmoidal transition for it. Halfway point is a glass transition. Right, so that's simple. Basically, if you cool it down any faster than that, this has kind of residual strains and stresses in it that get locked in. And basically, if you heat it up from the glass, you'll see that those relax. And when those relax, there's an enthalpy associated with it. So it's a transition that has zero enthalpy, but these kind of locked in structural things give rise to something that looks like an enthalpy transition. So it'll look like it'll have this, but it'll have a hump on it. And that hump has to do with the speed that you cooled it. The faster you cool it, the bigger the hump. So there's a plot of that somewhere here. Someplace here. Here. So these are different cooling rates. Oh, I guess this looks like it's backward, but the faster cooling should have a bigger peak on it. It looks like these are backwards, but basically the faster cooling has a bigger residual relaxation, whatever. So the slow cooling, it'll eventually get to no peak in it. That's for boron oxide loss. But anyway, so there's that business. Let me go back here. Like I said, there's a bunch of topics in here. So the first thing is like, why does it have a peak when you go through the melting point or go through any transition? So it could be an insulator conductor transition. It can be Schottky defects. Like he goes through every possible weird transition in the world. I mean, at least in metals, right? So most things, it's a crystalline melting. That's kind of what you're looking at. But it could be a liquid crystal, like when you have a display, a liquid crystal to random transition that has a heat. Could be a protein going from a native state to an unfolded state that has a heat. So actually, beyond metals, you could list like 20 different transitions for weird things, for goo, basically, right? So anyway, there are other, he goes for mostly metals and ceramics, but there are kind of soft matter also has transitions too. They're equally weird. So, and you can also equally measure them and kind of discuss it, but so this is the concept of the peak. So as you're heating it up and getting near the transition, the entropy. So you're looking at the change in entropy, the rate of change in entropy, right? So the rate of change. So it starts with a lot of entropy and it's going to like a crystal. So it's going, or it's let's see, starting as a crystal, it's going to a melt, and it's the rate of change of the entropy is kind of like the internal energy thing. Like it's got an increasing rate, like the slope increases as you go towards transition temperature because the rate of increase gets more and more rapid until you reach the transition temperature. And at that point, all the randomness you're going to get, you got. So in other words, it starts out perfectly ordered, say it's a crystal, and then it starts to change, so it's going to be disordered. So the rate of change from ordered to disordered is very rapid at the beginning. And then finally, there's no more disorder to get. Everything's just blown apart. It's random. So it's just static then. So this rate of change of entropy drops to zero. That's the idea. So there's a maximum point where you have the maximum rate of change of entropy. That's why you get a peak in the heat capacity that you see here. That's kind of one way to describe why you get that peak. It's the entropy change that's going on through the crystallization that drives it. That's the point, right? So anyway, so mathematically, if you want to do that, you say you have like Boltzmann functions, the energy over KT so that'd be like the probability of state melt and probability of state crystal. The ratio of those probabilities is going to be like that. If you say the crystal is the ground state, so E2 0, then this thing's 1, like exponential 0 is 1. So you just have that exponential as the probability of the random state. And then this kind of just rederives the, so you have two states, the random state and the other state. So the sum of states is just those two. And then that becomes the partition function, which normalizes the energy. So if you want to know the energy, it's the energy times the probability of the energy, which is a Boltzmann probability, divided by the partition function, gives you that thing. And then that thing, that derivative of that energy gives you the Einstein equation, actually. So it's kind of another way to get the Einstein equation, actually much faster than the way we did it. But this is really talking about a transition. Right, so this is a couple things like in this chapter, he derives the same thing over again. Or this is in a different book. This is a Kittle book, right? But basically, this is talking about a transition, but he gets the same equation. So you get this equation a couple different ways. We got it a different way before, but you can get it just by considering a transition thing. Right, so this is the energy of a transition. So once you have that energy, then you can say like first terms, this is the Einstein equation, but defined in this terms of a transition with just the one energy. So then you just say like this thing decays with T because it's 1 over T, and this thing increases with T. So this thing leads off, it increases, and this thing decays after. That's another way to say why do you get a peak in math. So I think the entropy thing might be easier to understand, but basically this is a mathematical way. It's got two terms, one decreases, one increases. You get a peak. And the peak's kind of where the energy matches the energy of the transition. So like, in fact, this plot is just mapping out these equations, right? So then, so there's a lot of transitions. So he goes through like so many transitions in here. The metal insulator transition, this is for iron oxide. And basically, so for this transition, so the electronic contribution for the insulator, there's no electrons above the Fermi level. So the gamma for electronic is 0. And for the metal, it's got the metal's gamma. So the transition entropy change is going to be the metal times the transition. The change in entropy is just that. So then you can calculate kind of how this thing would behave. Anyway, this is a mapping out of iron oxide going through that insulator to metal transition. Let's see. Oh, no, this is right. Iron oxide going through that metal to insulator to metal transitions like at the low temperature down here. Then this thing also has like has a magnetic transition, order disorder transition, which means it's going to lose this thing, right? This magnon heat capacity, which means that so it goes through a transition where it goes from metal to insulator at really low temperature, and it's got this order to disorder transition, like a paramagnetic transition at a very high temperature. So that's got a peak in it. That's all. And he's just saying, like, you can break apart, the insulator metal transition, and you can break apart the magnetic contribution to it. And this diluent part, I don't remember what that part is. That's like just the difference between CP and CV, I guess. But anyway, so there's 3 parts to it that they can add up to get the heat capacity dependence of this iron oxide. That's it. So it's anyway, this has like 2 topics to it. One topic is the metal insulator, the other topic is this magnetic order disorder thing, right? So, and then there's this so in this cobalt oxide material, you transition from tetrahedral to octahedral metal atoms in it. So it's kind of not a crystal transition, but a kind of a transition state transition for the metals in it, which gives rise to a peak also. So it's just, these are just like various kind of enthalpic transitions that you can find in metals. I mean, I think that's the theme of this late part of this chapter. And then this is ceramics. You have like NaCl. You can have 2 defects, a Schottky or Frenkel defect, and those will have also have a peak in the heat capacity. So in a Schottky, you lose the crystal will end up a hole for the metal, and also a hole for the chlorine, whatever. Right. So you end up with pairs disappear. So you don't have a missing charge in it. You just have 2 holes in it. So it's a paired hole missing for this. And that, in other words, you heat it up and these defects start to show up. That's a transition. That would show up as a heat capacity transition. And the Frenkel one, the metals are smaller than the halides, and then they group together. They can jump over and miss. So you have a hole showing up. So temperature will drive that kind of a defect too. So you have these 2 kinds of defects in these salts. They give some examples of the ones that work for that. All right, so it gives a peak. These 2 salts have that kind of peak due to the Schottky defects, so the thing where you're grouping up where you lose, like as you heat it up, these defect like holes show up in the crystal. That's the idea for the anyway, and that has a transition enthalpy that you can calculate by the same method. Like this is the Einstein, and then this is the kind of the density of states. So the density of the whole states and the natural state. So basically you can use the same method to calculate all these transitions. That's the idea. We're kind of using the Einstein equation and putting in whatever the density of states would be. to get the heat capacity. This is just a component of the heat capacity associated with that transition. You also have the basic, like the by temperature heat capacity added to that. All right, so what else? That's the equation for that. I'm not sure why this is here, except this is interesting, but it's a transition, like you get a mobility transition in these salts, but there's no plot of the heat capacity for it. Basically, it's another kind of transition. And the importance of this is that if you want to make a, like lithium ion battery has a liquid phosphate electrolyte in it, right? And that causes a lot of problems. It's a phosphorus fluorine thing that can blow up. It's electrolyte that kills everyone. And not that people are dying from it. Basically, when you hear about lithium ions blowing up, it's because of the electrolyte is liquid and it touches air, makes HF gas, nasty stuff, dissolves your bones. One drop will dissolve all your bones. If you're working with HF, make sure you have this calcium gel with you, because then you can immediately, like if you get exposed to it, you just cover yourself in this gel and it'll preferentially goes to calcium. So you can suck up all the fluorines. If you don't use that, water won't help. Nothing will help. You're dead. You become jello. And you need HF, like if you're working with silica or titania and you want to get the elemental composition, the only way to dissolve glass is to use HF to dissolve it. So if you're doing ceramics work, you have to use it. You have to be careful when you're using it, but you have to use it. There's only no other way. Then you do a mass spec on the solution that you make with it, right? But anyway, so you have to use it sometimes, especially in ceramics. So if you do use it, make sure you have that gel with you. Like I would carry a bottle of it in my pocket. Anyway, that's why you'd want to have a solid electrolyte, not have this fluorinated stuff around, right? So if you can make a solid electrolyte with this silver iodide salt, and then if you heat it up above this transition, again, it'll have an enthalpy transition. And all of a sudden, the silver ions become mobile, and the iodide remains in a lattice. The silver ions become like electrons, like an electron, the Drude model for electrons. They like fly around, so you can conduct the silver through this. Or if you're using the sodium sulfur battery, then you use the sulfur, right? So you have these silver atoms flying around a sulfur. So it's a solid crystal, but above that transition, they're completely mobile, as if it was a liquid. So you don't have to worry about it leaking or like the thing blowing up exactly. Sodium, so you have to run it at a high temperature though. That's the problem. Like the conduction transition for this thing. So the enthalpy that you're going to observe is going to be at like 300, 400 C. So it means your battery always has to be at 400 C. So basically the sodium sulfur battery has a higher energy density than lithium ion battery, but it has to operate at 400 C above this transition temperature. So you have mobile silver atoms. So that's a drawback to it. And also when you're at that temperature, you get dendritic growth of sodium across the electrodes and it short circuits and blows up. Maybe it doesn't blow up, but it kills the battery, right? So this could be, because sodium is in salt water and sulfur is in oil or whatever. It's all over the place. We have tons of sulfur, tons of sodium. It's not like it's limited like lithium. So anyway, this could be to solve the energy problem, but it's got these two defects. It has to run at high temperature. And then also it's got these things that grow across it, dendrites that short circuit it. Anyway, but you can calculate, you can get a heat capacity thing for that too, and use Einstein and do the same thing. Then there's this business of this liquids and glasses. So basically, so if you look at the entropy, you can calculate, you can get the curve for the entropy of a liquid and a curve for entropy of like a glass or a solid or a crystal, right? If it's a crystal. So then if you plot it out, so you can supercool the liquid, like if you don't have any nucleation sites, then you can supercool it, like I showed you with water, and then you whack it and it would crystallize. Basically, you can get a supercooled liquid. So you can calculate the entropy for that, and you have a curve for both. But if you extrapolate the liquid down to a very low temperature, you find out that you could have a liquid with a lower entropy than a solid. which isn't possible, right? Because a liquid always has to be more random than a solid. That's kind of what the definition of a liquid is, right? So that thing's called the Kautzmann paradox when that happens. All right, so if you before you get to that, so say you're on the supercooled liquid, then you form a glass. Like you form a glass at that point, and that resolves this paradox. So the reason why you have to get a glass is because if you cooled it anymore, so this would be like if you cool at a fast rate, fast rate, you get to lower and lower temperature transition, and finally you get to this point of no return, and that would be like the thermodynamic absolute glass transition. Otherwise, the glass transition is a moving target. If you cool it slower, it's higher, right? So it isn't a fixed number like a melting point. Anyway, so Kautzmann came up with that. I think it was like early 1900s, a long time ago, right? So anyway, so people are still looking at that, and they look at things like anyway. So it has to do with the heat capacity. That's why it's here. Like a derivative of this is going to give the heat capacity, and then you can get these weird. I don't know. He talks about this weird heat capacity behavior. I don't exactly get it. It's for selenium. It's something I've never worked with, but anyway, just the idea of the Kautzmann thing is important. And then so yeah, so he's getting like these transitions for the glasses, like there's just a peak that shows up that you don't know what it's from, and then it's from this what's called, so these aren't like you have harmonic, like a spring vibration, and then you have anharmonic, means there's a loss in it. So all these glassy things are going to have like a loss. In fact, the definition of how the glass works is through this viscosity equation. So you have like Arrhenius behavior, the viscosity should go with temperature following this kind of Boltzmann thing, energy over kT. So the lower the temperature, the higher the viscosity, right? And it's going to follow an exponential dependence. That's true of almost everything, right? So true of glasses too, except that if it's a normal Arrhenius behavior for glasses, this is a kinetic picture of what a glass is. So if it's going to, so if you do log of viscosity by the zero viscosity, you just get E over kT. So if you plot over T, it should be a straight line. That's a normal glass. It's called a strong glass. But many glasses don't follow that behavior. They have this deviation where the viscosity goes lower than what it should go. So it's a much more rapid dependence. So this is this fragility number they call it. It's a power. So it's a scaled exponential to some power. And that M would be less than 1 usually. So if it's like 0.8, that's called a fragile glass, right? So basically, if you look at all the glasses, the normal glasses are following along the straight line, and then this fragile glasses are going to deviate from it, and then just like water doesn't really form a glass, so it's the steepest one you could get. So things that are really super fragile don't actually form glasses, right? The things that are slightly deviating form glasses are called fragile glasses. All right, so there's this fragility concept of the glasses. It has to do with this entropy. This is the entropy difference between the liquid and the glass normalized by at the melting point, what it would have been. So the bigger that entropy distance, the more fragile the glass is. Anyway, there's a paper online that talks about that. It's kind of interesting if you're interested in that. What else? This topic is in the chapter too, but it just isn't exactly pointed out very well. So this is weird because it's a plot. I'm not sure where I got this, but basically it's fragility. This should go from 1 to 0, which it does kind of here for this glass fragility in alpha, but that's the kinetic fragility from the viscosity. That should go 1 to 0, like it's 1 when it's not fragile, and it's less than 1 when it's fragile. Anyway, I'm not sure about this plot, but there's 2 ways to get fragility. One's through thermodynamics, through the heat capacity, and the other one is through this kinetic measurement. And the 2, I guess, agree with each other. People that do this are kind of nutty. Like the French do this a lot, and there's people in the Navy that do this, Naval Research Lab. There's a whole lab that just does fragility of glasses, the Naval Research Lab. In NIST in Washington, people did this for a long time. Then they moved out from that, and they moved to different universities around the country. So it's probably like 100 people in the US that are looking at fragility of glasses as a main topic of their research. And in France, there's probably 1,000. So I guess there's probably been a Nobel Prize in it. I don't know about it. So anyway, it's a topic. He puts it in this chapter. It has to do with heat capacity. There's a thermodynamic way to look at it. There's a kinetic way. Anyway, I don't really think it's that important. Some people do, and I'm not sure there's no like device that people have made. There's not any kind of technology that you would do with this, except that it's a topic that people are working on, so you should know about it. Like you should know the word fragility in the context of glasses. And one is the number that would be like normal glass, and everything else, the weird glasses would be like a number smaller than that. This M, so it's about what you need to know about it. If you're interested in it, you can do more, but anyway, so this is the polymer part. So so this guy, like in the paper, they said, let's see, who does this? Is it Wunderlich or something, right? I think is the one, yeah, Wunderlich. So this guy was like the thermal, like in the 1960s, 70s, 80s. Anyway, he was at RPI in New York, Albany, and he was like the king of DSC measurements on polymers. Like he invented almost all the stuff, And he's mentioned in that paper on graphene and diamond, right? He's the guy that they cite. This says there's a transition in the temperature. So somehow he also did graphene and diamond, but he's a pretty famous guy. Didn't win the Nobel Prize or anything, but for polymers, for heat capacity, for thermal transitions. Anyway, so basically what they're saying, so if you think about the chain, it's just like in the kind of the Einstein model, you have the beads and the springs. So basically they just say, oh, you can use the Einstein model for a polymer chain. And they have kind of so they say, yeah, that's true until you get to low temperature, then you need to use the Debye model. That's the theme of this. So anyway, so you add up the molecules on the chain. This is almost like group contribution method. Like you're going to take each of the groups and they're going to each have a theta associated with it. You can figure out each of the vibrations of the chains. You can have like a table of 42 atomic group modes of vibration for polystyrene. So it's a pretty simple molecule. So the Scotch tape container, the tape's a polyester like PET, and it's got a glue that's an acrylic, and then this case is polystyrene, the clear case. Right. So if you want to know what polystyrene is, I think everyone's had interaction with that. Anyway, so anyway, how many atoms? 16 atoms per thing, and then you have an equation that decides like how many vibrations you'll get, 3 times the number of atoms minus the skeletal mode vibrations, which is 6 on this. And then you get a number 42 vibrations, and these are the Debye temperatures, or these are the Einstein temperatures for each of those 42. And the 42, some of them have the same energy. So you have this multiplicity of each. So there's 4,000, there's 8 of them, 2,000 is 10. So you take all those and sum them up. The energies, each one would be an Einstein equation energy with the theta plugged in, and you can get the heat capacity, right? Or you can follow this Russian guy who said, you don't need to do that. I have a cheat method. So he has a cheat method that has this cheat equation that's much simpler. Right, and then so you can calculate that for so this is this Tazarov compared to the Einstein thing. But anyway, the X's are Wunderlich's measurement for the heat capacity, and the lines of these theoretical. And I guess the advantage is you can break apart the components of the heat capacity. So you can see CP and CV are like almost the same, right? It's almost like not worth worrying about the difference given the scatter and the data points. And then they match at low temperature, they're exactly the same because the difference is proportional to T. So right here, CP minus CV is proportional to T right there. And they have this B, looks a lot like the Grun-Eisen parameter. But in fact, it is the Grun-Eisen parameter. They're not using gamma, they're using B. They got sick of gamma. So anyway, so for polymers, you can calculate the heat capacity. That's the point. I mean, theoretically, it fits in with all the metal stuff. So it just jumps off it and says like you can do the same thing for polymers. If you consider like a 1D along the chain heat capacity, and also 3D would be a Debye. So it's like a cubic equation. This should be squared somewhere. So anyway, after you integrate, you get t cubed here, and here you get 1/t², if you do it right. So anyway, it's just to mention that I think this isn't. The Palmer people are worried about other things, I think, in this now. At some point in the 70s, 80s, I guess, there was a whole group doing heat capacity, and one like had like 10 students, so enough to become faculty. So it grew, somewhat, but basically eventually they all ended up doing something else, like recycling plastics or something different, So anyway, so that's that. That's the end of this, what I have for this heat capacity thing. The next chapter is looking back at the equation of state stuff, and then except in the context of the things from the heat capacity. It's like taking the Boltzmann Bose-Einstein distribution and then using it to get just the mixing law. This is another, like we did 3 ways to get the X ln X term. There's a 4th way. You can use the Bose-Einstein distribution and get it. And then you can, from that point, you can kind of go on to some other things about how you make those mixing laws like more complicated, So dealing with real systems. So anyway, so that's what the next chapter is about. So that's about it. So if you have problems with the homework, let me know. Email me, I guess everyone's turning it in tomorrow. I guess the dates changed. So I actually didn't put a new one up, so I'm behind too. So I guess we're on Wednesday. Anyway, there's only like, next week's Thanksgiving, so we got Wednesday, and then the week after that's last week. I'm not sure what I'm gonna do, if we'll have a homework or just the final. Probably have a homework. I'll have one more homework and a final. The final is like 2 homeworks. It says, how many is that? 1, 2, 3, 4. 4 homeworks. The last one's 2 homeworks. So should be okay. Maybe, I don't know, I'll have to decide what to do for the last one, but so anyway, tomorrow, and I'll try to do 12:30 instead of 2. Because no one can make it at 2. All right, anyway, yeah, he never actually came back and said like it was okay. I saw him at a meeting, he said, oh, I'm here tomorrow.